Look at the image on the screen. Doesn't it look like a sort of a maze or something? What do you think it is? It is the fingerprint of a human being. These fingerprints are what the police and the CID use to catch the bad guys at the crime scene. From the crime scene, they collect the fingerprints and then they match it against the list of suspects to catch the bad guy. Now, let me tell you an interesting fact. Every human being in the world has their own fingerprint, their unique set of fingerprint. So that means millions and millions of patterns of fingerprints. Let us consider another example. You must have gone to the zoo and seen zebras. You must have noticed the intricate stripe patterns on the body of the zebra. Did you know that every zebra has a unique set of stripe patterns? And there are millions of zebras around the world. So that means there are millions of stripe patterns around the world. Similarly, every wave has its own unique characteristics. These characteristics, known as wave parameters, are used to measure the wave and distinguish one wave from another. So what are these wave parameters? Let us find out. The first parameter that we will talk about is a cycle. Now notice the animation on the screen. Here we see that at time t equal to 0, that is the dotted line, the particle is in rest position. Now when a slight disturbance is applied, the particle starts moving up from its mean position. So in the presence of the disturbance, the particle keeps moving up, goes till a certain distance and stops. Now remember, every particle has a tendency to return to its mean position. In this case, the dotted line. So when the particle reaches the top, it starts coming down towards the mean position. It comes down, reaches the mean position, but it does not stop because the disturbance is still present. So it continues moving downwards. It goes down till a certain distance and then stops. Like I told you, that every particle has a tendency to return to its mean position. So from the downward position, it starts going back up again. It goes back up, reaches its mean position, and then continues going upwards. So this entire process, as is being shown by the graph on the right hand side of the screen, is called a cycle. Even in the case of a longitudinal wave, the particle is at rest position at the center, as we see from the bottom animation. When the disturbance is applied, the particle moves forward. When the particle moves forward, it goes a certain distance and stops. And like I said, it has a tendency to return to its mean position, so it comes back. It comes back, crosses the mean position, and goes backward because the disturbance is still present. It goes till a certain distance and stops. And it wants to return to its mean position again, so it starts moving forward again and reaches the mean position. For a longitudinal wave, this is known as a cycle. So what is a cycle? A cycle is that after which a particle starts repeating its motion. So we talked about one of the wave parameters, that was a cycle. Now let us talk about a second wave parameter, that is a wavelength. In this picture, what do you see? You see a green wave and a red wave. From the start point of the green wave to the end point is known as one wavelength. Similarly, from the start point of the red wave to its end point is known as one wavelength. So how can we define a wavelength? A wavelength is basically the distance traveled by the wave in one cycle. Recall what I told you about a cycle? A cycle is that after which a particle repeats its motion, and wavelength is the distance traveled by the particle in one complete cycle. Now what happens in the case of longitudinal waves? As you recall from our previous lecture, in a longitudinal wave, the particles are vibrating to and fro in the direction of propagation of the wave. So in a longitudinal wave, we define a cycle as that after which the particles repeat their motion. And you know that in a longitudinal wave, the wave travels in the form of compressions and rarefactions. So in this case, we define a wavelength as the distance in between two compressions, two consecutive compressions, or the distance in between two consecutive rarefactions. So what is the definition of a wavelength? The wavelength of a wave is the distance traveled by the wave during one cycle. And how is wavelength represented? It is denoted by the Greek letter lambda. Now I have a question for you. In this picture, you see there are two waves, a wave shown in blue and a wave shown in red. So which wave do you think has a longer wavelength? The longer wavelength in this case is of the blue wave. Why? Recall what I told you about a wavelength. A wavelength is the distance covered by a particle during one complete cycle. So in the case of the blue wave, what is one complete cycle? It starts from this point and ends at this point. And in the case of a red wave, what is one complete cycle? It starts from this point or this point and ends at this point, or in this case, this point. So which one do you think has a longer wavelength? Obviously the blue wave. Now we talked about wavelength and cycle. Are there any more parameters to define waves? Let us find out from this animation. We perform a simple experiment where we tie a rope to a fixed end and hold the other end of the rope in our hand. Now, as we move the rope up and down in a vibratory motion, we notice that the rope is displaced from its mean position. So the disturbance, the displacement on either side that is taking place is known as the amplitude of the wave. That is the maximum displacement of the rope on either side of its mean position. So here is a picture to clear out the concept of amplitude. Notice these black dotted lines that have been shown. This black dotted line represents the amplitude of the wave. The amplitude of the wave is nothing but the maximum displacement of a particle on either side of its mean position. So that was the case for a transverse wave. How can we define amplitude in case of a longitudinal wave? You will recall that longitudinal wave travels in the form of compressions and rarefactions. So in the case of a longitudinal wave, we can define amplitude as the distance in between two particles in a rarefaction. This is the amplitude of a longitudinal wave. Now I have another question for you. On the screen, you see that there are two waves represented by green and red. Can you tell me which one has a greater amplitude? Yes, the greater amplitude is owned by the green wave. Why is it so? If you recall the definition of amplitude, it was the maximum displacement of a particle from its mean position. So what is the maximum displacement of the green wave? The displacement of the green wave is, as I showed, by the green arrow. And what is the displacement of the red wave? The displacement of the red wave is what I'm showing by the red arrow. So which one do you think is greater? Obviously the green wave. Now I have another question for you. Which of the following do you think has a higher amplitude? The sound of a police siren or the sound of a doorbell? Now let me tell you before I answer this question that for waves, if a wave has a greater amplitude, it has more loudness. And if it has lesser amplitude, it has less loudness. Now which one do you think is the correct answer? Obviously, the police siren. Why? Because as you all know from daily experience, you can hear the sound of a police siren from a long distance afar, even if you're in your house. But in the case of the sound of a doorbell, you cannot hear the sound of a doorbell if you go away from your house. So clearly, the sound of a police siren has a higher amplitude. Now let's take a look at this video. Here you find few kids playing with a slinky. Now notice the disturbances as they travel from one end to the other. You will find that some disturbances are traveling faster and some disturbances are traveling slower. So this particular characteristic can be used to distinguish between two waves. That is, some disturbances travel faster than other disturbances. Now consider this animation that is being shown on the board. Over here you find that 6 cycles of the wave are being completed in 3 seconds. So how can we calculate the time period from this? Now the time period is nothing but the time taken to complete one cycle. So in the previous animation we saw that there were 6 cycles being completed in 3 seconds. So we have 6 cycles being completed in 3 seconds. So one cycle will take how long? 3 by 6 seconds or half a second. Thus, we see that one cycle is completed in half a second. So how can we define time period mathematically now? Time period is nothing but the total time taken by all cycles divided by the number of cycles. You can see the definition on the screen. The time taken to complete the cycles divided by the number of cycles. Now let us consider the same video again. You will find that when the disturbances are traveling faster, more number of disturbances travel from one end to the other than when the disturbances are traveling slower. Lesser number of disturbances are traveling in this case. So we can distinguish between waves using this property as well. Now consider the same animation again. Here you find in 3 seconds, 6 cycles are being completed. So how can we distinguish waves using this property? This property is known as frequency. Now we define frequency as the number of cycles in 1 second. Consider the wave in the animation that we saw. In that we had 6 cycles being completed in 3 seconds. So in 3 seconds we have 6 cycles. So how many cycles do we have in 1 second? 6 by 3 or 2 cycles. Now the unit of this 2 cycles is 2 second inverse. Mathematically, second inverse is also known as hertz, and hertz is the unit of frequency. So we saw that in 3 seconds we got 6 cycles. Therefore, in 1 second, we have 2 cycles. So how can we mathematically define frequency? Frequency is nothing but the number of cycles divided by time taken to complete the cycles. You can see the mathematical formula as given on the board. Now I have a question for you. Let us solve a mathematical question to get the concept clear. The question says 600 cycles of a wave pass through a point in 1 second. So calculate the time period of the wave. Can you solve the sum? Now, what have we here in the question? In the question, we have been given that the number of waves, the number of cycles of a wave passing through are 600. So, from our previous discussion, we learned that time period is nothing but the total time taken to complete the cycles by number of cycles. So, the total time taken to complete the cycles has been given as 1 second. And what is the number of cycles? The number of cycles are 600. So 1 by 600. 1 by 600 is the time period of the wave. If you calculate this mathematically, the answer comes out to be 0.0016 seconds. That is the time period of the wave. Now we've talked about wavelength, cycle, time period and frequency. Now you must be knowing that cars and bikes and buses that you see on the road have a particular velocity. Did you also know that waves also have a velocity? The velocity of a wave is given by the distance traveled by the wave and divided by the time taken by the wave to travel that distance. Now, for calculations, we consider, as we see on the board over here, the distance traveled by the wave in 1 cycle is 1 wavelength. And what is the time taken to complete 1 cycle? 1 time period. So we can define wave velocity as wavelength upon time period. Now, if you recall from our previous discussion, frequency was nothing but the inverse of time, or likewise, time was nothing but the inverse of frequency. Thus, we can also write lambda by t as lambda into f. That is, velocity of a wave is given by wavelength times frequency. Now let's do a sum to get the concept of wavelength frequency better. The sum says, calculate the wavelength and time period of a sound wave of frequency 480 Hertz. The wave velocity of sound has been given as 330 meters per second. So how do we solve this sum? We have been given that the frequency of the wave is 480 Hertz. So the time period, as I mentioned, is 1 upon f, that is 1 upon 480, that is equal to 0.0028 seconds. Now we have the velocity of the wave given as 330 meters per second. And what have we been asked to find out? We have been asked to find out the wavelength. Now what was the formula for velocity? Velocity was lambda into f. Now we know the velocity, we know the frequency. What we have to find out is lambda. So lambda, or the wavelength, is nothing but v upon f. What is v? V was given as 330 meters per second. And what is f? F is 480 hertz. 480 hertz. So cancelling common factors, we get the wavelength as 33 by 48 meters. If you calculate that mathematically, that comes out to be 0.6875 meters. So 0.6875 meters is the wavelength of the wave. So let's take a quick summary of what have we learned so far. So far we learned that there are 4 wave properties: cycle, amplitude, wavelength, time period, and frequency. So let's take a quick recap of the definitions. Cycle of a wave is that after which the wave particles start repeating their motion. Amplitude of a wave is the maximum displacement of the particles from their mean position on either side. Wavelength of a wave is the distance traveled by the wave during one complete cycle. Time period of a wave is the time taken by a wave to complete one cycle. And frequency of a wave is the number of cycles that are completed by the wave in 1 second.